All right, we're moving to chapter 4 now. Should have this video up today, Friday, and should be taking our next test by Monday. I'll email you guys that as well, but just so you guys see this in the video here. So, chapter 4 has to do with probability. And what's probability? We're going to get into just focusing on, for now, just the basic concepts of probability. So, you can think of probability of the chances of something happening. So if you're trying to find the probability of something, you want to see what's the possibility that it's going to happen. Like, what are the chances that it's going to happen? You might hear like 50-50, a 50-50 chance. You might hear like 100% chance. You hear all these different things. I'm sure you probably heard people say 50-50. That means you have a 50% chance of something occurring. And what are these things that are going to be occurring? Well, those, we call them an event. So an event is any collection of results or outcomes of a procedure. So for example, let's say you're flipping a coin. The coin could possibly either land, and hopefully you answer this question in your head. It can either land heads or tails. So each one of those is an event, because each one of those is a different outcome. You can either land heads or you can land tails. Those are outcomes. So that's how we call them events. A simple event is an outcome or an event. So it's just building off the idea of an event. So a simple event is one that cannot be broken down any simpler, any further. And we'll look at an example, a more detailed example of what I mean by you can't break it down any further. But then we're going to have something called the sample space. So even though this says sample, don't get that mixed up with how we were describing what a sample was when we were talking about data, like collecting data, analyzing bar graphs, pie charts, mean, median, modes, all these things. It's not that type of sample. It's actually, when you say sample space, it mimics more how a population works. Because a sample space, it contains all possible events. So it says there, the sample space for a procedure consists of all possible simple events. So I just gave you an example of flipping a coin. So heads and tails, those are individually are simple events. They're events, and they happen to be simple as well, because you can't land heads different ways. When you flip a coin, there's only one way it's going to land heads. There's only one way it can land tails. It can't land heads different ways. If you flip the coin more times, you could possibly land heads more times, but that doesn't mean it's going to land head. It's not going to, coin isn't going to bend. It's not going to all of a sudden have a different head. And there's that, none of those things. So it's a simple event. And a sample space in that situation would be a set containing both heads and tails inside of it. So sort of listing out all your possible events as a group in using like set notation. And set notation are the little curly braces, if you don't remember. But that's what a sample space is. It just contains all the possible events for a particular procedure or whatever experiment that someone is doing. Maybe someone's doing an experiment trying to find a probability, or you're actually doing a procedure like you're flipping a coin, or maybe you're rolling dice. Those are actually procedures that you're taking to see what are the chances of something happening, which is, again, is probability. So don't mix those up. An event is just the possible outcome of some procedure that's being done. Anything. You could be picking a card out of a deck. There's 52 cards in the deck. There's different types of cards in there, and every time you pull out one card, each card that you get has its own outcome, because it has its own possibility. So that's what an event is. A simple event just breaks a little further, saying that that outcome has no more characteristics to it. There's nothing else describing that outcome. If you get heads, that's it. There's no other way to do that. And the sample space is just a collection of all of them together. So for example, here I said a little more detail. Simple events. Let's say you give birth to one kid and the result is a girl. That idea is a simple event because you can't have two kids inside of one. I mean, yes, you can have twins, but when you're just looking at one kid, that kid it can't be different things. The kid is just it's gonna be a girl, or you're gonna have a boy, or what have you. But there's no different ways that you can have this kid. There's only one way you're going to have one kid. And same thing with rolling a single die. Let's say if you're gonna roll, if you guys if you don't know what a die is, let me show you. So here I just Google. Here's the die. This is what I'm talking about when I say a die. So let's say if you're rolling one of these, a possible outcome is 5. There's no other way to roll a 5. That's why it's a simple event. Because however many times you roll this die, every time it lands on 5, it's going to be the same 5 every time. There is no other possibility. There's nothing else can happen. So that's what's a simple event. If you're thinking about a sample space, that would be all possible outcomes together. So if we saw that die, it's possible that it can land on 3 or it can land on 6. Or right now it actually is, if you can see the picture, it is on 5. But this one's on 4 and so on and so forth. There's 2, there's 3, there's 6. It's a cube. So there's 6 sides to this cube. And you can either land 1 or you can land a 2 or you can 3 or 4 or 5 or 6. And all those are simple outcomes. The collection of all of them together, that's the sample space. The sample space is listing all the possible outcomes. So before you even roll a die, you already know what are the different outcomes that can happen. And all those possible outcomes make the sample space. One of those outcomes is an event. And if that event can be broken down any further, that's a simple event. So you don't have to worry so much. I'm not going to be nitpicky on well, that's a simple event, that's an event. As long as you understand what an outcome is. And those are events. What's a possibility? So here's something that's not a simple event. So for instance, let's say instead of having one kid, you have 3 kids. And yes, there's only one way that you can have those 3 kids. Can't have a kid a different way. You have pregnant and you give birth. That can only happen one way. So with 3 births, the event. But now, if you have 3 kids, yes, each individual one. Like if you just have one, that's a simple event because there's no other way you can have them. But we all know there's a big difference between you being the oldest or you're the youngest or you're the middle child. So when you're having 3 births, there is not just you either have all girls, all boys, 2 girls and a boy, and then 2 boys and a girl. Like you also have to think about the scenarios of, well, what if the girl's the youngest or the girl's the middle child, and then the 2 boys, one's the oldest, one's the youngest, or vice versa. What if the 2 youngest are girls and the boy is the oldest? Or you have a girl, then the boy's the middle child, and then another girl's the oldest. There's different scenarios that if you're just trying to see, if you're planning to have 3 kids before you have these 3 kids, you're trying to see, well, what are the chances that I'm going to have a boy first and then 2 girls, or then I have a boy, then a girl, and then a boy again. So the order in which you have them, we know is important, because there's a difference between being the older brother, older sister, or younger brother, or younger sister. So that's not simple because it can happen in different ways. If that's confusing, this next one I think is helpful. Let's say, for example, let's say you have 10 numbers, so the numbers from 1 through 10 on a hat, and you're trying to see the probability of getting an even number. So the outcome of an even number is not simple event. And the reason why it's not a simple event is because the even number can happen different ways. So if I'm picking a number out of a hat, numbers 1 through 10, well, 2 is even, so that's a possible outcome. 4 is even, that's a possible outcome. 6, 8, and 10 are possible outcomes. So there's not just one way that a number can be even. There's different even numbers. So that's why if you're trying to select the even number, that's not a simple event. Because if you're choosing from 1 to 10, 2 would be a perfectly good answer. 6 would be a perfectly good number. 4 would be a perfectly good number. 10 would be, and 8 would be perfectly good numbers. So even wouldn't be simple because there's different possible outcomes. If you're just looking for the even number 4, now that would be a simple event because you can't have 4 multiple ways. There's only one number 4, but there's many even numbers. So that's the difference between how a simple event could be the number 4, whereas a not simple event is trying to choose an even number or odd number, where things can happen. There's different odd numbers, there's different even numbers. So that's just some terminology understanding. Hopefully you're getting the idea of what an outcome is. So here's how you would list your sample space, and this is what I meant by the braces. So those braces mean set notation. So in the first one, the procedure that we're talking about is having one birth. So if you're going to have one kid, there's only two. Having a girl is a simple event. Having a boy is a simple event. Listing all the possible outcomes, that's your sample space. All the different possibilities. Like I said, rolling a fair die. We know you can land a 1 or 2, 3, 4, all the way up to 6. So you would actually list, if you're trying to write the sample space of rolling a die once, then you would have to write all the different outcomes. That's 1 through 6. Now, where you have 3 kids, this is that what I was talking about, that sometimes the boy might be the oldest, the girl might be the oldest, the youngest, and so on and so forth. That order really does matter. So there's a difference between having all boys, 2 boys and a girl, boy, then a girl, then a boy, or a boy, then 2 girls, or a girl and then 2 boys, and back and vice versa. There's a difference between that. So just because you're having 3 kids, that doesn't mean there's only 2 possible outcomes. Because you can have a boy first, and that can happen multiple ways. Because you can have a boy and then a girl, or you can have a boy and then a boy and then another boy, or you can have a boy, and then a girl, and so on and so forth. There's different ways that can happen. So it's important you understand the context. So event is a possible outcome. A simple event is just an outcome that can't be broken down any further. And the sample space is the collection of all of these outcomes that we get. Here's some notation. So again, first we're trying to just understand, what does probability mean? What are we looking for? And trying to see what's the chances of something happening. And here's some notation that we use for probability. So the capital P, that denotes probability. So if you're trying to find the probability of something, that's where that capital P comes in play. Now, what you're trying to find the probability of, so again, I can say I'm trying to find the probability of landing heads. So P, I would use capital P just to denote I'm trying to find a probability. But A, capital B, capital C, and then, again, just for general sake, maybe I'll put a capital D and F, but normally we use A, B, C. Those are the outcomes. So flipping a coin, A is a possible outcome. Heads, which could be A, is a possible outcome. Tails, which could be B, is another possible outcome. So P is just denoting that you're doing a probability, where A, B, C is the actual outcomes that can happen. Now, put P in parentheses A, so you can read that P of A, so the probability of event A occurring. So that's what you're trying to find the probability for, and the probability of A happening. So you can try to find the probability of landing a 3 on a fair die, or so on and so forth. There's so many different type of ways to see this, but the idea is probability. You're trying to find the chances of something happening, and those different scenarios of what can happen are the possible outcomes. And a sample space is just a collection of all of those possible outcomes. And then when we're talking about probabilities, it's really important to know that probabilities only exist between 0 and 1. If we think about like percentages, right? Percentages are from 0% to 100%. And we're going to make that connection with something later. But for now, just know probabilities can only exist between 0 and 1. Where 0 means that it's impossible, that it's never going to happen. Where a half, 0.5, that's a 50% chance of happening. And a 1 is like saying 100%. So that means that it's exactly like you know for a fact it's going to happen. That's 100%. The closer you are to positive 1, the more likely it is for something to happen. Like there's a 95% chance that so-and-so is gonna happen. Or the closer you get to 0, the more unlikely an event is not going to occur. And then, of course, being in the middle, there's equal chances of each outcome happening. So remember that, though. It's really important. Probabilities are only and strictly between 0 and 1. And that's what this is denoting here. That the following three are so we're going to talk about how we can actually calculate a probability, but just to reinforce, don't forget, probabilities strictly only exist between 0 and 1, and including 0 and 1. So 0 is a perfectly good probability, 1 is also a good probability. There's no, and everything else in between, of course. So there's these 3 different approaches to actually calculating probabilities. One of the first ones, which is really building off something we've done before, is the relative frequency approximation of probability. So we've done relative frequencies before. That's just taking the number of frequencies in one row and dividing it by the total number of frequencies in a set. And that's what this is essentially doing. We're, instead of, in the case what we were doing before, relative frequency involved looking at how many times that particular class or category happened. So that's why the number of times A occurred. So A is a particular outcome. And maybe you're trying to see what happens. For instance, you can flip a coin 100 times. And out of those 100 times, maybe 47 of those times landed heads. And let's say you're trying to find the probability of landing heads. You flip the coin 100 times. And all you do is you just analyze it. You do like a frequency table. You have heads and tails. You know that you say you flip it 100 times, you can tally up. Every time, let's say you flip a coin, you land heads, you put a tally on heads. You flip a coin, you land heads again, you tally on heads. You flip a coin a third time, and you land tails, and then you put a tally mark on tails, and you do this up to flipping the coin 100 times. And by then, you're going to have a certain number of heads and then a certain number of tails. If you wanted to find the probability of landing heads, you can look at your data. If you know that you flipped the coin 100 times, then that means your denominator is going to be 100. Remember, your numerator is the number of times A occurred. Again, it just depends what you're trying to determine. If you're trying to see the probability of landing heads, just count how many times it landed heads over however many times you flipped the coin. If you did it 100 times, then you divide it by 100. If you want to find the probability of landing tails, then you'd have to look at your chart that you made and see out of those, see how many times did you get tails. So then you take however many, let's say it was 38 times you landed tails, and then you divide by however many times you actually made the procedure, meaning you flipped the coin 100 times. And that's going to give you and that would be the relative frequency approximation. So this probability is not, we're not trying to conceptually understand the probabilities. We're sort of using information that we know from before, like actually looking at what has happened. Normally you calculate probabilities beforehand. Let's say if you're an insurance company or life insurance company, they already have these formulas or algorithms that help them determine how much to charge someone when it comes to car insurance. So just something to think about. Alright, don't know why I made the reference of car insurance, so scratch that. Again, relative frequency, depending how many times the procedure occurred, that's going to be your denominator. Your numerator is how many times that particular event you're trying to find the probability for actually happened. So give this a shot. Try it. So find a quarter, find a penny, flip a coin 100 times, and in one column put heads, in one row put heads, in another row put tails, and actually write out of those 100 how many times did you get heads, how many times did you get tails, and then try to find the probability of each one. Find the probability of landing heads, find the probability of landing tails, and email me what you got. Again, answers are going to vary because sometimes you're not going to have heads the exact same number of times as somebody else, and you might. But the idea is I'm going to have slightly different answers. But try doing this and then email it to me and let me know what you got. Now, here is the classical approach. This is probably the one that you're used to. For example, if you're trying to find the probability of landing heads, well, most people know that as there's a 50% chance of landing heads, because the classical approach just looks at the number of ways A can occur. So the previous one is the relative frequency approach. That one was I actually flipped a coin and I counted to see how many times I got heads. Where in this scenario, all I think about are, well, what are the possible outcomes when I'm flipping this coin? So the denominator is a number of different simple events. So we know when we're flipping a coin, there's only two possible outcomes. So in other words, your denominator ends up being your sample space. We know that there's only two possible outcomes when you flip a coin. And from those two outcomes, only one of them is heads. So then that would give you 1/2, which is a half. So that's what I'm saying. Try flipping a coin 100 times and test this. See how your answers vary between the classical approach and the relative frequency approach. The classical approaches we're more used to. The idea is you have the total possible outcomes in the denominator and how many times that particular event can occur. Like if you're rolling this die, this one that we're looking at before, we know that this die has 6 sides. The 6 different possibilities are 1, 2, 3, 4, 5, and 6. If you're trying to find the probability of landing just a 4, hopefully you pause the video to think about, well, what would this probability be? Again, if you're doing the relative frequency approach, you actually have to roll that die like 100 or 200 times. And then actually now there's going to be more categories, because now you have to check, well, you're going to have a category for when it lands 1, a category for when it lands 2, a category for when it lands 3 or 4, 5, 6, 7, so on and so forth. Oh, sorry, 6, 7. 1, 2, 3, 4, 5, 6. Each of those categories will have its own row. If you try actually rolling this die 100 times, if you have one, you can try it. See how many times you get 1, see how many times you get 2 and 3 and 4 and 5 and 6. And then if you're trying to find the probability of just landing 4, you count how many times you actually rolled 4 divided by 100, because you rolled that die 100 times. Or you can use a classical approach, which we know all we have to see is the number of different simple events. In other words, is just the total number of possible outcomes. We just said that you can either get 1, 2, 3, 4, 5, or 6. So there's 6 different possible outcomes, and that would be your denominator. Your numerator, like I said, we're trying to find the probability of rolling a 4. And there's only one way to get a 4. It can't happen other ways. So that probability, it would be 1 over 1, because you can only land 4 one way, and over 6 because there's 6 different possible outcomes. So that saves us some time on rolling the die 100 times, but if you want to try it, you can, to see if the probabilities match up, since both of them are different ways to calculate a probability. Where this one's more of an approximation, and this one gives us a better idea of the probabilities. Another way to look at this classical approach is, like, let's say you're trying to pick a number out of a hat. There's 10 numbers in that hat. Numbers from 1 through 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All those numbers are inside the hat rolled up. And you're trying to find the probability of rolling a 2. Again, the denominator is the total possible outcomes. If it's a hat and you're picking from this hat, and the numbers in this hat are number 1, number 2, number 3, number 4, number 5, number 6, number 7, number 8, number 9, number 10, then there's 10 possible outcomes. But you're trying to find the probability of giving an even number. So now you have to think about, well, how many ways can I get an even number? Remember, the numerator doesn't always have to be a simple event. The denominators have to be the simple events. So if we look at the numbers between 1 to 10, I did say earlier that 2, 4, 6, 8, and 10 are all even numbers. So 2, 4, 6, 8, and 10. That's going to be our numerator. So our numerator would be 5, because there's 5 different even numbers between the numbers 1 through 10. And then my denominator is 10, because there's 10 possible outcomes, 1 through 10. So your probability would be 5 over 10. And with fractions, if you can simplify, you always should simplify. And keep that in mind. So that the 5 over 10 would be a half. Meaning there's a 50% chance that you're going to choose an even number when you're picking from a hat from numbers 1 through 10. And again, if you want, what does that mean? Was there a 50% chance of that occurring? Well, let's say you were picking from a hat 40 times. A 50% probability means that from those 50 or 40 times that you selected something, like I said, let's say you did something 40 times, you know the probability of something happening is 50%. That means if you do something 40 different times, of those 40 times, 20 of them is going to have the event that you calculated your probability for. And that's the whole point of this probabilities. They give us percentages. They give us the likelihood of something happening. So then we go and make decisions based off of that. let's look at an example of this, of both of them. So, for instance, let's say, suppose that the survey asked 500 families with 3 children to disclose the gender of their children and found that 180 of the families had 2 boys and a girl. So again, it's not specifying if it had the youngest are 2 boys and the oldest is a girl. It doesn't say they have 2 boys and a girl. It's just they have a combination of 2 boys and 1 girl. And they got that information, but they had to go ask 500 families to see this. So if we use the relative frequency approach to find this probability of having 2 boys and a girl, well, the relative frequency approach actually involves you doing a procedure, which they kindly gave us the procedure here. The procedure was asking 500 families. The same way I asked you to flip the coin 100 times and count how many times it landed heads and count how many times it landed tails. And then you can do relative frequency probabilities using that. Here they did that work for us. They actually searched 500 families, and 180 of those families had 2 boys and 1 girl. And again, you're hoping that they chose these 500 families in the best manner possible to give us the best percentage of what can happen. And then we'll see the answers to this, but I want to compare these 2 questions side by side. So let's calculate. Using the classical approach, find the probability of having 2 boys and a girl. Alright, this changes things up a bit. So we have to think about, the formula tells us, the number of ways A can occur divided by the total number of outcomes. So we have to think about, if we're going to use the classical approach, we're trying to find the probability of 2 boys and 1 girl. So our event in this situation, the outcome that we're looking for, is having 2 boys and a girl. We have to think about how many ways can that happen. If we go back to our chart that we made, well, here we see that there's actually, with 3 births, again, if you're having 2 boys and a girl, that means you're giving birth 3 times. Unless you had twins or triplets, but let's say if you had 1 kid at a time. If you were having 3, these are all the different possible outcomes. You can have a situation where you have all boys. There's a situation where you have 2 boys and then your last kid is a girl. Or you can have a boy or a girl and a boy. Or you can just have a newborn, which is a boy, and your 2 oldest are girls. You can have a girl, a boy, and then a girl. You can have 2 girls and then the boy is the oldest. Or you can strictly have all girls. But there's a total number of outcomes. There's 1, 2, 3, 4, 5, 6, 7, 8. Again, they actually asked 500 families, and 180 of them had a combination of 2 boys and 1 girl in the house. Now, if we're using the classical approach, well, we have to think about the numerator is how many ways could that event occur. That event that we're talking about is 2 boys and 1 girl. So if we go back to that chart, we can actually see how many of these scenarios have 2 boys and a girl in them. There's 2 boys here and 1 girl. There's 2 boys here and 1 girl. This has 2 girls, and here is another one that has 2 boys and 1 girl. In this situation, the girl is the youngest. So there's 3 different ways that can happen. But then to find the probability of it happening, then you have to divide by the total number of possible outcomes. And we know that there's 1, 2, 3, 4, 5, 6, 7, 8. There's a total of 8 possible outcomes. But how many of those 8 are involved having 2 boys and a girl? Well, we said only 3 of them. So hopefully you're trying to calculate these, and if you need to stay on this a little longer, again, press pause. You can try to figure it out. But we're going to continue. So here, the relative frequency approach, again, just takes the number of ways the event actually occurred. The classical approach is you're trying to think of how many ways something can occur, where the relative frequency approach is you actually go do like a small experiment or a procedure, asking 500 or 1,000 or checking 1,000 different datas, and then dividing by how many data values there are. In the numerator, you're going to have however many fit the procedure or the outcome that you're looking for. So they had 180, that gives us 0.36. In the other scenario, we know there's 8 possible outcomes. There's different ways you can have 2 boys and a girl. Again, one could be older, younger, so on and so forth. But the total number of possibilities is 8. We know there was 8 possible outcomes, but only 3 of those 8 actually involved 2 boys and 1 girl. So that would be using the classical approach, and the other one would be using the relative frequency approach. So when you're doing your homework, just watch out for that. They're usually giving you questions about like studying 500 people, 300 people, 200 people. Usually you might resort to the relative frequency approach. But the classical approach always works as long as you know all the possible outcomes and the different ways that the numerator can occur or the event can occur. So that's something to think about when you're doing these. And now this is the third way. So we looked at the relative frequency, the classical approach, and now there's the subjective probabilities. The subjective, like how it says in its term, it's subjective. So those are probabilities that, let me just give you an example. For instance, I know the probability of me, Gonzaga, giving birth to a baby is 0%. That's a subjective probability. I know the probability is 0. I cannot give birth to a kid. That's 100% true. That's my probability. There's a 100% chance that I'm not going to give birth to a baby. Or another subjective probability that there's a 0% chance that the Lakers are going to win the Super Bowl. So the reason for that is that basketball teams don't play in the Super Bowl. Football teams do. So I know that basketball players are not playing in the NFL. Hence, the probability is 0. And that's the idea of subjective probabilities. You're coming up with probabilities using, of course, some type of knowledge and giving a percentage for that. So subjective probabilities of the event A is estimated by using knowledge of the relevant circumstances. Again, I don't know much about basketball, but I know more about football. And I know only football players can play in the Super Bowl. So that's why I made the question set up that way, that the Lakers will never win the Super Bowl. And that's 100% accurate. And those are the idea of subjective probability. There's a knowledge that you have that gives you an idea of a probability. Now, when you're dealing with probabilities, again, you saw in my answers here. Here I wrote 2 decimals, here I wrote 3 decimals. Again, if you can leave it as a fraction, that's best for me. So when expressing the value of the probability, either give it the exact fraction. Again, sometimes I'd rather have the exact fraction because that's the exact probability. Once you start getting to 2, 3, 4 decimal probabilities, where did I put that?